Piezo-Transducers. So here I would briefly cover introduction to the structural health monitoring, especially how it is relevant to civil engineering structures, and of course similar kind of thing would apply to other multidisciplinary domains. And here I would focus on the mechanical impedance approach for structural health monitoring using piezo sensors. I would augment that with application concerning joints, steel joints under static type of loading, and some of the new practical developments in the field of structural health monitoring using piezo sensors. In civil engineering domains, structural health monitoring has already evolved as a very important part, especially in the research community. Now everyone is very much concerned that we should do health monitoring, because whenever a structure fails, we come to know that it could have been avoided. There are numerous examples where we have the structures which are still running, and where people have identified they have some or the other vulnerable components. For example, Acton, he has given this example of these kind of bridges where we have cantilever span, and they are holding a suspended span in between, and essentially the entire load from the suspended span to the cantilever ones is transferred by these four anchor pins. So they assume a very important and very critical role, and if any of them gives away, then this may lead to disaster. Similarly, we have the problem of vulnerability to fatigue. So fatigue is essentially, even if the magnitude of the stresses is not very large, but their fluctuating nature is very detrimental to the structure. And one more thing of concern is the determinate structures. So in determinate structures, especially where we have no redundancy, so their monitoring is in more significance. The definition of structural health monitoring by Acton is that it involves measurement of operating and loading environment. So this is the measurement part. Why? To track the symptoms or operational incidents, anomalies, and deterioration or damage indicators that may affect the operation, serviceability, or safety reliability. So these are the principal things involved in structural health monitoring. So this definition essentially is from the point of view of civil engineering structures, but it can be well extended to other type of structures also. So why do we emphasize on structural health monitoring, especially for civil structures? These are the obvious reasons, so that we are able to detect structural damages in proper time, and we can take remedial actions. We as civil engineers, we do a lot of design, but we seldom do validation. This is also very important. We should do that. The evaluation of structure after retrofitting, it's very common now. We do a lot of retrofitting of civil engineering structures, so we must do some measurements to validate that. And of course, the conventional approach of visual inspection is not going to be that much effective. And if we have these kind of measurements in our civil structure especially, then we can have a lot of data which will be of great value to structural engineers. Now here I would focus health monitoring of especially for fatigue life assessment using piezo sensors, and especially here we are using the electromechanical impedance technique. Now piezoelectric materials, they are smart materials because they show stimulus response characteristics. We apply stress, what we get is the development of charges. And conversely, if we apply an electric field, what we find is that they undergo deformation. And by this converse effect, we can make the structure excite also if we bond the piezo patch to that. Now commercial forms, there are competition between the ceramics and the polymers. And ceramics, they obviously have a lot of advantages, and they have come out to be more acceptable type of sensor. Now here, as I showed in the previous slide, we have the direct effect, which can utilize the piezo patch as sensor. Then we have converse effect, which we can utilize as actuator. But there is one more thing, that is the use of the direct and converse effects in synergy, which has come out as electromechanical impedance technique, or in short, EMI technique. Now how this technique works because it essentially involves the principle of vibrations. So it makes the structure vibrate, and only difference from the global vibration techniques, which are the conventional health monitoring techniques for the bridges, is that here the frequencies employed, they are very large in the kilohertz range. And because here the high frequency is deployed, so the sensitivity of the technique comes out to be very good and typically comparable to that of the ultrasonic techniques. So here the application of the technique is not very difficult. We bond a piezo patch on the structure and excite it through a commercial impedance analyzer. So in this configuration, the patch, it dynamically interacts with the structure and it collects the admittance. So admittance captures essentially the dynamic characteristics of the structure in the form of a signature. So here essentially the piezo patch acts both as sensor and actuator. And because we employ a very high frequency, we have the stress waves which are typically in centimeter to millimeter range, and they are quite sensitive to the occurrence of any damage. So one advantage is that we get typically high sensitivity, and the other, we can say either is limitation or advantage is that the sensing zone of each patch is somehow localized. So this helps in damage localization. Now the sensitivity is quite high. We have acquired the signature of the structure in the frequency range. This is from 140 to 150 kilohertz, and if there is any damage to the structure, the signature gets changed in a very recognizable form. We have done extensive experiments in the last decade, starting from 2001 to 2004. Concrete, this technique came to be applied on reinforced concrete structures, and in fact our group was one of the first few to apply the technique on reinforced concrete structures, large reinforced concrete structures like bridges. And the first experiment, it showed that typically the technique can detect cracks much before they become visible to the naked eye. So here we put the piezo patches, they could detect the cracks in form of the shift of the signature before they were visible. So I am not going in too much detail, but similar observations we could get from model studies on frames, reinforced concrete frames. Concrete is a very troublesome composite material. So here we could get the capture the occurrence of damage much prior to by other means. For example, here you can see that signature started changing, and the cracks, they were visible at number 6 stage of the loading, whereas the piezo patch, it provided a much earlier warning. So these and other studies, they have further motivated research, and typically here what we measure is the inverse of the electrical impedance, that is admittance. So admittance is the main function which we plot as a function of frequency. So it typically has two components. One is the real part and the other is the imaginary part. So real part, we can see a very obvious reflection of the dynamic characteristics of the structure, and the imaginary part, typically it is used for sensor diagnostics, because when we are using a sensor for health monitoring, the stresses are also transmitted to the sensor, and it's also possible that sensor may also have some kind of debonding, or it may have deterioration, or it may break. So these things, diagnostics, they are provided by the imaginary part. In conventional EMI technique, typically the quantification of damage was not very rigorous, or not very based on the dynamic characteristics, dynamic parameters. It was rather based on the statistical variation of the signature. For example, in the structure which I have just shown concerning the frame, this is how the root mean square division of the signature goes. So it provides some kind of indication, but it does not quantitatively tell us that how much is the change in the stiffness or how much is the loss of stiffness. So this value, for example, root mean square deviation, this can vary from patch to patch, from structure to structure. So there is no fixed scale. So this was the main problem. Now this problem can be very easily addressed if we follow the mechanical impedance approach. So here we do quantification not based on the raw signature but on the parameters derived from the signature. Now these are some of the earlier models because here we have to use some kind of model to obtain the mechanical impedance parameter. So the earlier models were the static approach, then Liang's model came in 1994. So Liang, he proposed 1D model, and the subsequent colleagues, they came up with 2D model also. So essentially the interaction of the piezo patch in a real structure is two-dimensional in nature. But here the 2D models, the problem was that if we want to extract the mechanical impedance of the structure, then the equation does not give us opportunity to do so. So I addressed this problem in 2004, and we came out with a new impedance approach where a single term, it sort of represented the two-dimensional interaction between the patch and the structure. So now this equation is suitable. We just do our required manipulation and we can obtain the mechanical impedance of the structure. So here we have the quantity which we are measuring, in fact is the admittance, and this is related to mechanical impedance of the structure. So mechanical impedance is the main thing, just like the dynamic stiffness, and if we can obtain that, we can get better information about the structure. So what we propose that before bonding the patch on the structure, we first obtain its signature in the free form and we update its model, and then we bond on the structure and then further use for health monitoring. So this essentially improved the performance of the technique, because we are using a better model for our patch. So essentially the data which we are getting from the patch, we are not just relying on the model provided by the manufacturer, but our own model, and this gives us better quantity which we are going to measure. So all we need to do is just use this equation and solve it with a complex equation. We are measuring two parameters, the conductance and susceptance, G and V, and basically we can break this complex equation into two equations and we can just find the mechanical impedance. Now, how these two parameters they vary, that provided us very interesting insight. Now, if we compare with very simple combinations of basic elements, stiffness, the spring, the damper, and the mass, they follow a certain trend of the variation of the real and the imaginary parts. And to our surprise, when we checked how the mechanical impedance we extracted from a structure, it varied. The real and imaginary parts, they were conforming to one of these sort of basic setups. For example, here this was an aluminum block, and within this frequency range, we found from the experimental measurements that the behavior was just like a spring damper system. So we were wondering what these two parameters they make. Are these absolute values, or what happens with damage? So with damage, we found a very perfect correlation that when damage is happening on the structure, these parameters are accordingly changing. The identified stiffness is going down, mass is going down, and the damping is going up. But however, what is the correlation between these parameters and the actual parameters of the structure? That was the next question. So here I demonstrated with the help of a recent study. This is a joint project between IIT Delhi and University of Technology, Sweden. So here what we started with a few specimens of typical prototype joints. These are double lap specimens. Here the plate sizes are typically 200 by 100 by 5 mm. And these specimens, they were subjected to fatigue loading. So we bonded in each specimen 3 piezo patches in same configuration, and total number of specimens was 3 in numbers. So we have one plate which is one which is being monitored here, and then we have the two plates left on the other side. Now this table shows the loading history. So here we quickly kept the stress values from quickly 0.08 times the yield stress to 60% of the yield stress, and the specimen failed at close to 63,000 cycles, and this is the failure mode. Now this is the second specimen. So here essentially the configuration is more or less similar, except that we have reduced the thickness slightly by 1 millimeter, so that we can go higher to the stress value. We can increase the stress value to 0.88 times the yield stress. And then this is the third one. So here we have essentially same configuration, and here we could go up till 130,000 cycles, and here the stress values were typically over 90% of the yield stress. And here we get failure plane exactly at the force location, and here now these are the three piezo patches. We monitored the stiffness loss also during the experimentation, because we get the load versus deformation data. From there we could monitor how the stiffness loss is happening. Now if we do conventional damage quantification by means of this root mean square division of the signature, then we are at disadvantage. For example, we have total 9 piezo patches. Now if we see this kind of plot with the increasing cycles, we don't get any kind of very well defined correlation. For example, if we see the magnitude, these 3 piezo patches, they were on the same specimen, but they are giving different magnitudes. And here we see a lot of scatter of the data. And now just the first specimen itself, patch 1, 2 and 3 which are shown here, 1 is at the top, 2 and 3 they are bottom. So 2 and 3 they are at same distance from the failure plane. However, the magnitudes they are starkly different. So this prompted us that we should go for the mechanical impedance approach rather than this one. And piezo patches, they identified the structure as a parallel combination of spring and damper system. This is experimental observation, because now we can see here that the real part which we get from the sensors have identified now this system for the structure. The real part is constant and the imaginary part is negative and going like this. So this is characteristic of the this kind of system. And one very important observation came here. Now here what we have done, we have plotted inverse of the frequency with the imaginary part. And what we can see here, the slope of this basically is measure of the identified stiffness. And it's very clear observation now that as the cycles they are increasing, the stiffness identified by the piezo patches going down. So this is not the absolute stiffness, this is the stiffness identified by the piezo patches. So here we have rejected two piezo patches we have rejected, first specimen and the last specimen. So 2 patches they were rejected because they did not fit the diagnostics. The diagnostics suggested that possibly we have a case of debonding. So their data was rejected. Now based on all other piezo patches, the observation is very consistent.
5 more minutes please.
And to sort of find how the stiffness loss by the piezo patch it correlates with the actual stiffness, we have plotted for first specimen we had less data, so second we increased the data, and third one we deliberately increased the data more, and we could find that we have reasonably quite acceptable correlation between the stiffness identified by the piezo patch and the absolute stiffness of the specimen. So what this shows that if we want piezo patches and we don't bother to measure the absolute stiffness, we can have something very meaningful data right from the piezo patches. So we quantified in a non-dimensional form the stiffness loss. So here this is not the absolute stiffness but the piezo identified stiffness, and the correlation plots they came in a very narrow band with the exception of one of the piezo patches. And we could very easily write a regression equation also for these three specimens. So from here we learn that now the piezo identified stiffness, this correlates very well with the actual stiffness, and the residual fatigue life, this can be sort of quantified by this kind of calibration. And here I just have few slides which cover some of the new practical developments. Now first one describes how the piezo sensors, they can possibly also be used to replace accelerometers for the global vibration techniques. Now piezos, if we just make use of their direct effect equation, which is this one, and if there is no electric field applied from outside, then the equation becomes very simple, and we can put it in this form, that the voltage output across the piezo patch is directly proportional to strain. And here we are getting a sensitivity of something around 200 millivolts per microstrain. Now from the comparison of three sensors, here we have the plot from the piezo patch and compared to accelerometer. Now the piezo patch and accelerometer, they measure different quantities, one measures strain, other acceleration, but they fit, if we are going in the frequency domain, they can both serve same purpose. Now what we find from this kind of comparison, that if I give 100 marks to accelerometer, then the response from the piezo patch, it will get at least 95 marks. But now from the cost point of view, the piezo patches, they offer a very strict competition to accelerometers. And how we can replace accelerometers in totality? For example, for health monitoring, if we want the piezo patches in this coupled form. So here I am not talking about the EMI technique which I described previously. Here I am just talking about the global vibration technique. And if the member is under flexure and we have this kind of coupling between the patches, then the voltage output we get from the combined coupling is basically a measure of the curvature. Because here the combined voltage will be proportional to sum of the strains, top and bottom. And this we don't need very expensive equipment for this measurement, and this can serve as health parameter, because curvature has been very well established as a very sensitive parameter for the damage, especially for global vibration techniques. And this is the plot which my student here got from simple beam, simply supported beam. So damage location can be easily identified. So I am not going into much detail, but just I want to highlight that coupled piezo pair, it can also enable the same sort of damage detection capability which accelerometer, which is very expensive, that offers. We also have developed a variant of the piezo patch which can be embedded inside concrete structures, and if we have this kind of embedded sensor, then it can remain protected throughout the life of the structure, and it can provide us a lot of data. Now this is the comparison between accelerometer and the concrete vibration sensor based on piezo patch. Now we have also, in our lab, we have developed a dynamic force sensor, so which we have transferred to a company. So if you do this kind of integration between both the global and the local EMI technique, then this offers a lot of advantages. The combined system can be much better because it captures the advantages of the both. And then there are few low-cost adaptations of the EMI technique which we have also worked. In fact,
Dr. Suresh, I'm afraid your time is up.
So okay, I just jump to conclusions.
Please.